I will talk with you about how we actually can measure metallicity of Cepheids into the Milky Way up to the small Magellanic Clouds at the moment. First of all, I want to step back and to understand, which is the difference between an image and a spectra, because in principle we are looking at the same star map. How can we decide to have an image of the sky or to have a spectra? The main difference is that when we observe the sky with a telescope that only has a lens, we are collecting information, spatial information, both on the y-axis and on x-axis. So if we say a luminous spot in the sky, we can actually connect all that brightness with a point. And so we can say, okay, here there is a luminous galaxy, here there is a star, and stuff like this. And we collect all this information on the CCD. But what happens when we want indeed to obtain a spectrum? The difference that we have to do when we want to collect a spectra is to translate the spatial information into the wavelength. And how can we do this? This is doing with the grating. Indeed, when we observe with a telescope, the spatial resolution is given by the size of the telescope, because, as you may know, with the diffraction angle, we know that the radius of the telescope is linked with the theta, with the angle of this diffraction. At least, from the Earth, we also have the effect of the seeing of the atmosphere, but in principle is given by the radius of the telescope. Indeed, with the spectral resolution is given by this grating, because once that the light of the star is arrived on this grating, then is splitted into the wavelength. And for this reason, in these images, after this there is a rainbow, because in the rainbow the light is splitted all along the different wavelength. And another important point is that we can have two types of spectrograph. The first one is with the slit. This means, and with the slit we still can have information on the y-axis. This means that if we are observing a galaxy, still we can know which wavelength is coming and which light is coming from the upper part of the galaxies, because the light will travel only in the upper part of the slit and from the center of the galaxies and from the lower part of the galaxy. Another kind of spectrograph is done with fiber optics. With fiber optics, we lose all the information that we know about the spatial distribution of the light. But indeed, with fiber optics, we can obtain more spectra at the same time. This means that how much fiber we can place in the mirror, downside the mirror, how much spectra we can collect. And this is very important, because we can do multi-object spectroscopy, and we can also do integral field spectroscopy. That is a way to obtain, after the analysis, another time back the information about the spatial resolution. And I just presented you the spectrograph with fiber optics, because 3 weeks ago, I was lucky enough to go in Chile for the foremost science project verification, and here you can see a picture of the fiber placement. Here, foremost is a 4-meter spectroscopy facility that has been mounted on the ISO 4-meter class telescope Vista, and is made up of more than 2,000 fibers. These fibers then are linked to two different gratings, so we can have low resolution and high resolution spectra. And here, with these colors, you can see the position of the fiber according to the point that you give into the OB, into the description of the OB. And this is the distance of the telescope from the center of the object that you were pointing. And with this facility, for instance, you can do different science cases at the same time, because you can point every fiber to an object. For instance, you can point to stars, to start forming regions, to whatever you want at the same time. And you can have, with 20 minutes of observation, you can have more than one spectra. But now, let's see what happened, into the atmosphere of the star to create this spectra. First of all, we have to remember that the center of the star, the star is behaving as a black body. So, from the center of the star, there is some radiation traveling to the outskirts of the star. But what happened in the external layer of the atmosphere? We also have seen this morning that there can be some ions, some atoms, some molecules, and these for sure will impact the travel of the light, because light can interact with this. And so the light can be scattered because atoms and ions can be absorbed or can be emitted, and this sign will go into the black body radiation. And so we will see this signature, the presence of these molecules, as lines in the spectra of the star. In particular, these are absorption lines. This means that there was in the atmosphere of the star, in the external layer, was present, like for instance, an atom of calcium that absorbed the photon for the quantum mechanics at that specific wavelength. And so we don't receive that wavelength, and we say, okay, we don't receive that one because there was something absorbing. And also, after different tests in laboratory, now we can see which kind of lines, and so which kind of atoms are present in a different part of the atmosphere of the star, because thanks to atomic physics and to model of the stellar spectra, now we can say, okay, these, for instance, the iron one, that, because in astronomy we say iron 1 is the neutral iron, and iron 2 is one time ionized. We have this strange way of talk. So, okay, now we know from theory that iron lines are traces of the external part of the atmosphere. But to do this, we need also to study this into the laboratory system. And also, we can say that different kind of stellar and different stars, they have different spectra, because every kind of star has a different color. This means that in principle the black body solution is different because of the temperature of the core of the star is different, and because every kind of star has a different atmosphere that's related to the chemical composition. So every star, we expect a different spectra for every kind of star. For instance, like just for information, Cepheids are this kind of star, classical Cepheid, that in general they are this temperature, and in general they are rich on metal because they are population 2. This means that there was some time in the universe to become rich of metals, and this time is like the explosion of supernova that enriched the stellar medium. And so indeed, there are other stars that are poor of metals because they were formed, they are population 2, they were formed, like for instance, type 2 Cepheids and RR-Li, they were formed more time ago with respect to the classical Cepheids, and so they are more metal poor. Now, just to be on the same line, also Louise anticipated this notation. When we talk about metallicity abundance, we are saying the comparison of the metallicity, the abundance of one element with respect to the hydrogen, and then with respect to the solar value of that element. So this means that every time that, for instance, we are also, there is also solar physicists, and they are still trying to understand the metallicity, very precisely the metallicity of the sun. Every time that the metallicity of the sun changes, we cannot more do comparison with my metallicity that I measured today and some metallicity that someone measured 10 years ago, because they also refer to a different solar value, and this can be a source of systematic. Then, When we talk about metallicity, nowadays we talk only about the iron abundances, because iron is the most abundant element that can be found, and it's also very easy to measure because there are a lot of lines present in the stellar spectra. So a lot of times when we say, okay, this is metal rich, majority of the times we are only referring about the iron. And this is also the only metal that's important, together with the oxygen, for the extragalactic distance scale. Then we have to to be careful that the metallicity that we measure with iron is not equivalent to zeta. When we study like stellar evolution and we say, okay, we can say that a star is done of X, that's helium, Y, that's hydrogen, and Z, that's metal. But that Z does not correspond in logarithmic way to the iron. No, because that one is only iron. Then, sometimes we talk about nucleosynthesis and enrichment of the interstellar medium and stuff like this. And in that way, we are still referring to a different notation. That means an element, how much is abundant? An element with respect to the abundancy of the iron on that context. And like, for instance, sometimes we talk about alpha enrichment. This means that the elements that were formed thanks to supernova explosion. And this means how much do we have of that alpha element with respect to the iron. Sometimes we talk about like S-process enrichment. This means elements that were formed thanks to slowly process or to rapid process. So every time that we see these, we have to be careful of what we are seeing. But now, before I show you a stellar spectra, because I know that you are waiting for this, I want to tell you that we need to do two operations before observing a stellar spectrum. First of all is the normalization of the spectrum, because you have seen, and you also know that a black body radiation is not a line. There is a curve, but we don't like to work with this. Probably understood that we don't like to work with anything that's not linear. So, no, we don't. So we need to normalize the spectrum. And also because when we observe something that's arriving to a telescope and to a CCD, we are also taking into account the shape of the mirror, because the light that's coming, so taking into account also this, and we don't like this. And also the second thing that we need to take into account is the radial velocity correction, because you know something like the Doppler effect and something like this. So if a star is moving, and also we from the Earth, because I think that nowadays the only high-resolution spectroscopy that we can have is from the Earth. Also we are moving. So we need to take into account this, because otherwise, how we can know which line is what? Because the only thing that we have when we observe a spectra is something like this, the first part 1, with a lot of lines. But the only system that we know at which lines correspond which wavelength is the laboratory system. Because we don't know in a star that's moving far away from us with the velocity, we don't know what's the wavelength of that star. So we do the cross-correlation technique, and this is something that you have for sure to do to know which line is what. This means that we have a list of lines from laboratory lines, thanks to nuclear physicists and to atom study. We know that there are some elements, some molecules, some ions that they will form at that specific wavelength. So we have our spectra with observed lines, and we have the list of lines from the laboratory. And what we do is a cross-correlation. It's just a very simple things to do. We try to find the best combination for which the majority of the number of lines from the laboratory correspond to some lines that are formed in the spectra. At this point, we know, we hope that we know the right velocity of the star, and we do the correction. And the correction is just a shift with this formula. Oh, it's so small, but it's a shift with that's taking into account the velocity of the light and the delta lambda that we measure. And so we can move is like a simple thing that we do is to move all the spectra, the wavelength of the spectra, with this correction. So at this point, we know, for instance, we can also do this correction only with the two most important lights that we found almost everywhere, H alpha and H beta, because we know that number from laboratory. So if we know that H alpha is not at 4860, but it's shifted, we have to shift all the spectra because H alpha is like recognizable. And this is what we have to do. For sure, if we have more line, especially in the case of Cepheids, where lines, in reality, where lines are not lines, but they are more like big, we don't know the center of the line. So we need more line to take into account that we don't know the center, and so we can move very well this. And like, for instance, these are, for example, spectra of 3 different type 2 Cepheids, and you can see a different metallicity. Metallicity, that means iron over H. And you can see that, for instance, with going at lower metallicity, first of all, when we see minus metallicity, iron over H equal to 0, it's solar metallicity. Then the numbers that are minor than 0, we see that they are metal poor, because they are more metal poor than the sun. Indeed, this is a convention that we defined, because no one say that sun is 0, just we decided because we like the sun. And then we say that number major than 0, they are metal rich with respect to the sun. But sometimes we forgot to say with respect to the sun, because it's very important. So, like, for instance, you can visually see that going to lower metallicity, some lines of the iron, they disappear. They don't form anymore in the spectra of the star, because there are no such atoms in the atmosphere that are able to create that lines. And that's okay. You can also see other different elements, how they behave. And another thing that I want to tell you is that these 3 spectra not only differs about the metallicity, but they also differs for the temperature, for the surface gravities, and for the velocity. They don't have nothing similar. But now, once we have a spectra in this condition, and I also want to tell you that this number, only you know this number after that you have done the analysis, not when you receive the spectra. I put it here, the number for information, but in principle, you don't know when you observe what is this number. And indeed, these are the answers that you are searching for. But by the way, there are different ways of obtaining this number, like the curve of growth, the spectral synthesis, and also we can do this with neural networks. The curve of growth and the spectral synthesis, they are more classical way in which you have to observe and to work with one spectra, more or less with one spectra per time, and to search the stellar parameters for every star. Indeed, artificial intelligence and neural network, they need like a test, and then they need a trial sample, so they need more spectra, but they, for sure, this way and the way that people are trying to use this neural network will be more useful in the future when we will have an amount of spectra to analyze from different facilities, and so there will be, no more people, no more time to do all this work one by one. So it's also good if we try to implement this way. Indeed, I will focus only on the first two ways, also because the third way, the physics is the same. You just have to know the physics and to implement and to train a model in a way that you want to know. The things that we have to take into account, the ingredients that we will use in a spectral analysis are a lot, because we need to know in principle and to use some model atmosphere. And one caveat, as also Luis was saying, that different models that in principle we are using static models atmosphere to describe dynamic Cepheid atmosphere, because the fact that Cepheids are pulsating for sure impacts also the lines. And for instance, sometimes it's okay, we need at least in Magellanic Clouds, Large Magellanic Clouds, Martino, to observe Cepheids, he was observing for like 1 hour to reach the good signal-to-noise ratio of the spectra. But if a Cepheid has a period of 1 day and you observe it for 1 hour, for sure, I mean, something has happened in the pulsation. It's changing because, and so this is the first thing that you have to take into account. Then you have the atomic physics, because also the model, the line lists from laboratory, they are changing and they are improving. So if I analyze today one spectra with all this model of today, also my result will not be the same if I do the same work in 2 years and something changed. Then we have the line list and the spectral inclusion region, because I mean, also the line list, we have to take into account that a line list can be more complete in one wavelength respect to another, but we have observed a spectra in a specific wavelength, because when we observe a spectrum and we observe with a telescope, an instrument, we will receive only the light from that part of the spectra and of the visible, of the near infrared that we are receiving. And so we will have only lines in that part of the spectrum, but we need also to have a complete line list in that part of the spectra that we are analyzing to do a good correction in velocity. Then there is the continuum estimation, because as I've told you, we want to normalize the spectrum, and this means that we need to estimate the continuum of the black body and we need to remove that one. And so at that point we have a linear spectrum. Then we have to take into account the 0 point, the thing that I was telling you, that everything is expressed with respect of the solar value, and then the details of the analysis. And the details of the analysis are worse. I mean, worse than all of this, because they are linked to the observator, to the person that's doing the analysis, because, I mean, I can decide to keep or to not keep a line, something like this. For this reason, probably will be good also to have a machine learning technique, because at that point you just train an algorithm and the algorithm does everything. It's no more linked to our choose, because sometimes, I mean, observational physics is linked with the person that's doing, because sometimes you can only rely and trust on your eyes. My point of view can be different from another point of view. And for instance, another thing to take into account is that when we want to estimate, we want to use a line, not all the lines are the same, because, I mean, in the perfect world, every line has its position in the spectrum. In the real world, Cepheids are pulsating, star is moving. This means that the line is no more a line, but it's becoming bigger and bigger. So this means that two lines, the wings of two lines, can touch each other, as you can see here. And now, here, which one is the continuum here? Because in this point, there is some, flux that's taken from one line, from one absorber. Some other that's taken from here. Indeed, like for instance, this is not happening here, because more or less you can see, okay, here I can have a better basis for the continuum. And this is the same problem that in photometry you have with crowding, because in crowding the thing that you have to do to have a better PSF, point spread function, is that you have to remove the contribution of the other star, and here is the same of the other line, because I need to do a measurement of the line, of the flux in this line with respect to the continuum, not to the wing of another line. And so this is another thing to take into account. But however, with all this problem, we can receive a lot of information from a spectrum, because we can know the effective temperature, the surface gravity of the star, the microturbulence velocity, the chemical abundances, and more. Thanks to this information, Once that we link these that are stellar parameters and spectral parameters with other information that we know for the star, that for instance are the parallax, the proper motion, the position in the HR diagram, we can have a lot of information on the stellar physics, on the stellar interiors, and also on the history of the cosmos, because if I'm looking at an atmosphere of an old star, I know what was happening when the star was born at that point. But now, let's see what's the physics behind the curve of growth. Given the temperature, given the effective temperature, so the surface gravity and the velocity of turbulence, we can infer, once that we measure the equivalent width, we can infer the abundances of an element. So, the equivalent width is the area that I was showing you inside a line with respect to a continuum. So for this reason, the continuum was important, because the equivalent width is the flux that's absorbed in a line with respect to the continuum. The effective temperature is the temperature of the atmosphere of the star. The log G is a proxy for the surface gravity, because, I mean, this also impacts, because you can imagine that, for instance, for a white dwarf and for a classical surface, there are two completely different values of surface gravity, because one is a giant, so the atmosphere, the external layer, is not so linked to the core of the star, and another one is a a dwarf. So this means that the gravity of a dwarf is different, because the external layer of the dwarf is still well gravitationally linked to the core of the star, and it also impacts the formation and the emission of the light. So this means that the same equivalent width can give a different stellar abundances of that element. Then, in particular, what we do, also here you can see that according to the shape of the line, this means that the line has been formed in a different regime. But indeed, what we do in this method is to measure in an iterative way the abundances of that comes from all the iron lines, and then we try to fix all the parameters, the effective temperature, the gravity, and the velocity, with some minimization, in order to have at the end that all the iron lines give us the same abundances. And for instance, this is done by, for the effective temperature, we know one residual correlation between the iron abundances of a line and the excitation potential of the neutral iron lines. For the surface gravity, we want the same abundances for iron 1 and iron 2. And this is because we have seen that iron 1 line and iron 2 line, they are not formed in the same layer of the star. So this means that they are linked to the surface gravity in a different way. And their abundances should be the same, because they are the same element in the end. And so if we minimize this, we have a proxy for the gravity. Then the microturbulent velocity, that means that we don't have a correlation between the iron abundances and the equivalent width, because the microturbulent velocity is an effect that's broadening our line. Since the surface is pulsating, can happen that the equivalent width is modified, but the important thing is that the flux that inside the equivalent width doesn't have to change. And then, in the end, the iron abundances is the mean of each iron abundance that's coming from one iron lines. For this reason, when we have to pick the iron lines, we have to pick the iron lines that have a perfect wing and that have a continuum that's well measured. Otherwise, we are saying that the flux in the iron line is not only coming from the iron, for instance, but for instance can come also from the sodium, because there was a sodium iron that also a sodium line that also can be excited at that point. For this reason, I mean, here enter also the human being, because you have to choose from which line you trust the abundances. And like here, for example, we can see some method consistent check from the LMC cephates, and you can see here that there is no correlation among the effective temperature and the iron abundances for the cephates in the Large Magellanic Cloud. Also no correlation in the surface gravity, because this is the surface gravity, and no correlation in the velocity turbulence. And indeed, here you can see the same minimization, but in blue you have for the iron, the iron 1, that means neutral iron, and in orange you have for the ionized iron. And you can see that more or less the distribution of both the two species are around 0. So this means that the iteration is working well. And then here you have the difference of the abundances coming from iron 1 and iron 2. And this is an histogram of all the values, and you can see that they peak at 0. And for instance, if you want to know some more details about how to do this analysis, I can suggest you some paper, because in principle they have done the continuum normalization is done with Dowspec, and then the analysis of the line is done with the Gala from Mucciarelli et al. Dowspec from Stetson and Pancino, and Gala from Mucciarelli. By the way, after this, if you remember, cephates were important because they can provide also another observable that is the period. And you can see that the period is not dependent on that the iron is not independent of the period, but that the other quantity are dependent on the period, because cephates are pulsating. And so every time that the atmosphere is moving, all these other stellar parameters, they have to change. Because if the star is at its minimum, this means that the temperature is at its maximum. And if the star is at radius is maximum, temperature is minimum. And you have no way, you have to see this in your data. Otherwise, this means that you are not, your sensitivity is not good to work with cephates if you are not able to see this difference. And for instance, here you can see also the dependence of the temperature with respect to the phase, to the pulsational phase. And in principle, if these stars were observed with more criteria, because they were just observed with no prior on the phase, but you can still see that this is more or less like a light cube, because if you double here, you will have a light cube, and this is what you want, because as you see the light cube in the plot magnitude and phase, you have to see also the light cube in the plot temperature and phase, because temperature is a color, so you have to see that's changing also there. And this is okay. Then, for the spectral synthesis way of work of analyzed spectra, you are not only taking into account the equivalent width, but you are taking into account all the features of the spectra and all the features of the line. And in this case, in order to obtain a chemical abundances, you need to know a synthetic spectra, a temperature, a microturbulence, a log G, and also a velocity broadening. And in this case, you are not searching for all these parameters in one shot, but you need to do this in step by step. So the first thing that you want to do is to calculate the effective temperature, and a way to do this without passing through the curve of growth is to search for the effective temperature from the line-dip ratio. What is this? Is that, as we have seen before, there are, thanks to the atomic physics, we know that there are some lines that depends more on the temperature and on the potential to be formed, and some lines that depend less on that parameters. So if we do the ratio of the temperature coming from these two lines, in principle, we have something that is not dependent on the temperature itself and can give us an estimate of the temperature. So, like for instance, first of all, the paper of Kovtov and 2016, they calculate this coefficient thanks to a large sample of star where the temperature was known from other principles, like for instance for interferometry or something that was independent from spectra. And so they were able to calibrate this ratio. Then the ratio is just the difference of, the ratio is given by this one, the ratio of the two lines, where the D is the line depth of one line, and these are the line depth of the two different lines. So, and R is the ratio. So once we know the ratio, we can have an estimate of the effective temperature. The important point here is that, first of all, the two lines should be close enough into the continuum, so they have the same continuum estimation, and also if we don't have reddening effect, because if we are looking at a line that is in a certain wavelength and another line that is far away in the spectra, we can have some problem with the continuum definition and also with the reddening that's not working on the same way on that two lines, because also when we observe and when we take into account a spectra, we have always to remember that the light is passing through the interstellar medium, and so we have to work with the lines that are close enough that the reddening, for instance, has the same effect on that two lines. Because if you remember in the lesson of this morning, we say that the reddening is not working the same against, light in the red part of the spectra and in the blue part of the spectra. So for this kind of study, we need two lines that are in the same part of the spectra. So at least also if we don't correct for the reddening, we know that the reddening is doing the same effect to the both lines. And also because if we correct for the continuum, also if the continuum is not perfect, because it can happen that it's not perfect, but we are only seeing the depth with respect to the continuum in this region. So if the lines are close enough, it's okay for us. And then this method is only applicable for FGK stars with this effective temperature and also with the metallicity that were present in the Kotu et al. Paper, because this is like a problem of machine learning. If I train my model with this star test, then also, the star that I want to obtain result over, they have to be inside my sample. Otherwise, I'm just doing an extrapolation. So we have to take into account this. Then, if we want to measure the microturbulence from iron 1 lines, we have to measure the equivalent width for each of the lines. As I've told you before, we need to obtain the same abundances for every line. And so, thanks to a minimization, we can obtain an estimate of the microturbulence. That microturbulence is the value that minimized the mean value coming from different lines. And for instance, in this exam time, we are doing, first of all, one assumption on all the iron lines, because we are saying that the log G is not important. So we are giving, like, for instance, one fixed value for all the lines. And then, in this case, we are using the curve of growth method, because the physics is always the same, because what we are saying is that given that I told you that the log G should be 1, the effect temperature I measured in the step before, then I only have the abundances and the microturbulence, and so I try to minimize the correlation before these two, between these two. Then we also have to derive the surface gravity, and as I told you before, the surface gravity always come from a comparison between iron 1 and iron 2 lines, because these are the most popular lines that we can find in a spectral feature. And we know that they depend differently from the gravity. So once that they give us the same abundances, this means that we have found the right value of G. At this point, what we do in the spectral synthesis analysis is to take a stellar spectra from some models and to give to that stellar spectra the parameters that we are calculated in this way, and then to compare this with the observed spectra. And now you don't see nothing in this screen. But if you look on your laptop, first of all, there is one white line, I hope that you see that one, and it's the observed spectra. Then there is one red line, that's the stellar, the synthetic spectrum, the synthetic spectrum model that, some people just compiled in the 19, and they say, okay, this is a synthetic spectrum for a FG star. Then you say, okay, give me a synthetic spectrum for FG star with the TF log G and all the other things that you measured. And then you have the red spectra. That's the spectra, the synthetic spectra, that is more close to your observable, and their spectra is telling you the chemical abundances, because the code is telling you, if you start from a stellar spectra with this effective temperature, with this surface gravity, and with this V broadening, and with this velocity, you need to have these iron abundances in order to retrieve the line that you have in your observed spectra. So in the end, is a minimization between the synthetic spectra that's searching for different iron abundances and the observed spectra. Also, in this case, and this spectral synthesis was the analysis that I've done in the last few months with some spectra of type 2 Cepheids. And I think this is for the first time that we have a sample of 18 type 2 Cepheids in the Magellanic, in the Milky Way, and that we can have a period luminosity metallicity relation for type 2 Cepheids. As you can see also here, like for classical Cepheids, because the pulsation properties are the same, iron is independent of period, but still the parameters, they depend on the period, because also type 2 Cepheids, they are pulsating, and so the temperature, the gravity, and the velocity, they change during the pulsation cycle. Then, as we had seen also, as Louise was showing, and as we have seen this morning, we can just do a chi-square minimization to search not only for alpha and beta, but also to search for the gamma term for type 2 Cepheids. And what we do is to compare at the end the metallicity and photometric parallaxis with Gaia parallaxis. And also here you can also see that also in the case of type 2 Cepheids, we need to correct the Gaia parallaxis because there is a small offset. And in the end, what we obtain, but this is just a preliminary analysis, is that the gamma term, for type 2 Cepheids is negligible because it's comparable to the error. And this is also, first of all, because type 2 Cepheids, with respect to the classical Cepheids, they are old, so they are more metal poor. But this is also good because, if we want a good standard cadmium, we should have less systematics possible. So, this, is the end of my talk. These are the take-home messages that I want that you remember. The first thing is that spectra contain a lot of information about the stellar atmospheric composition, and that you can use spectra not only for this distance slide purpose. Indeed, these are, only a small drop in the ocean of things that you can do with spectra, because spectra can help you really to know everything about a lot about the formation of elements, very different elements. Then that you have to remember that every choice that you make during the analysis process can introduce systematics in your results. Then that the curve of growth links stellar parameters to the equivalent width. That this means that, for every temperature, gravity, and velocity that you have, an equivalent width is linked to an abundances. And if you change one stellar parameters, also the abundances will change. Indeed, that spectral synthesis fits the entire line profile, because with the spectral synthesis, you are comparing an observed spectra with a synthetic spectra. And then a takeaway is that a good standard cadmium should be affected by as few systematics as possible. So this is the end of my lesson, and thank you.